Hello, my name is Jacqueline Danso, and I'm a Banting postdoctoral fellow at the University of Toronto. I'll be talking about massive galaxies at high redshift, which have received a lot of attention recently, and specifically about the quiescent population at redshift 3 to 6. Massive quiescent galaxies at high redshift are very different from their counterparts in the local universe. This is a 10 to the 11 solar mass massive quiescent galaxy at redshift 3.7. It was discovered in deep near-infrared imaging from the Z-Forge survey in 2017. In addition to being very compact, massive quiescent galaxies like this are faint in the UV optical and emit most of their light in the near-infrared. Its K-band Mossfire spectrum reveals Balmer absorption lines typical of recently quenched or post-starburst galaxies whose light is dominated by A stars, which have lifetimes of 200 megayears to a gigayear. The plot on the right shows the stellar mass assembly history of this galaxy, derived by jointly fitting the photometry and Mossfire spectrum. The green line is the maximum mass of baryons allowed in dark matter halos with the same number density as massive quiescent galaxies at the observed redshift of 4. These blue lines here are lines of constant star formation. We can see that this galaxy assembled all of its mass between redshift 5 and 6. And in order to do this, it would have had to form stars at a rate of 900 solar masses a year, using up to 80% of the halo baryons. This is extremely efficient and rapid star formation, and it's very uncommon in the local universe, where galaxies only use up to 5 to 10% of their halo baryons. A few other observations of massive quiescent galaxies at high redshift, specifically redshifts greater than 3, have come out to corroborate this picture. However, there are only a handful of these spectroscopic confirmations. This is stellar mass as a function of redshift for all spectroscopically confirmed quiescent galaxies out to redshift 6. There are two things I want to point out from this plot. The first is that there are only a handful of spectroscopic confirmations at high redshift. In particular, there are less than 20 massive quiescent galaxies that have been confirmed with spectroscopy at redshifts greater than 3. And those that exist are mostly due to Keck, just to highlight how transformative this observatory has been for this science. Until 2020, there were almost no spectroscopic confirmations of quiescent galaxies at redshifts greater than 4. And this was surprising for a number of reasons. We had tens of photometric candidates at these redshifts, and the star formation histories of quiescent galaxies at redshifts 2 to 3 suggested that they should already be quenched or quenching by redshifts 4 to 6. So the answer then was one of two things. Either these galaxies don't exist at these redshifts, or maybe they do exist and we're just not sensitive enough. And if they do exist, can we reliably confirm quiescent galaxies at redshifts greater than 4 with ground-based spectroscopy? To do this, we need robust photometrically selected samples. Massive galaxies at high redshift are both faint and rare, so we need deep imaging over large portions of the sky to detect them. So that's what we did with the Phoenix survey. It's a 0.6 square degree program in Cosmos and UDS. The survey uses two custom filters that we installed and commissioned on the Flamingos 2 imager at Gemini South. And this method is similar to the Z-Forge and the new friend medium band surveys, which splits the J and H bands to detect massive galaxies at redshift 3. Here I'm showing the K-blue and K-red filters at the top, and at the bottom, a quiescent galaxy template at redshift 4.7 and a dusty star forming template at redshift 1.3. With the traditional K-short band, the two templates are identical. However, when we add K-blue and K-red, we're able to clearly distinguish between the two populations. This increased sensitivity to the Balmer break gives us precise photometric redshift estimates. These lines here show the predicted outlier fraction and photometric redshift uncertainties for different bandpass combinations. And we see here that the K-split filters reduce contamination from low redshift interlopers by a factor of 7 and improve photometric redshift uncertainties by a factor of 4. With the Phoenix survey, we uncovered 4 massive galaxies at redshift 3 to 5. These are located in one of our pointings in Cosmos. Here, I'm showing false color K-blue, K-red images of our targets. And for reference, a source that is flat in F-nu would be white. So these galaxies are red, which is evidence of older stellar populations or strong emission lines. On the left, I'm showing postage stamps of our galaxies in different band passes. The middle panel shows multi-band photometry from the Ultra Vista survey combined with that from the Phoenix survey shown in magenta here. Each of our galaxies has photometry in 30 to 51 bands, so the SEDs are very well sampled. We fit our galaxies with 2 SED fitting codes, Easy Pi and Bagpipes. You'll notice that our galaxies are faint or even completely undetected in F160W and have little to no flux in the rest-range UV optical. They also have red cable K-red colors, indicating the presence of a strong Balmer break. The cable K-red filters are also sensitive to strong emission lines. They identify the strong H-beta O3 emission in this broadline AGN. And these emission lines mimic Balmer breaks by artificially boosting the flux in the K-band. So objects like this can make it very difficult to identify bona fide quiescent galaxies. In 2 of our candidates, the cable K-red filters confirm the strength of the Balmer break and rule out lower redshift dusty star-forming solutions. And for all candidates, the photometric redshift solutions are consistent between the 2 codes. We observed our candidates for 11 hours on Mossfire. Here I'm showing 2D spectra and optimally extracted 1D spectra. The magenta line is the model fit to only the spectrum with the corresponding redshift solution shown in this panel. Redshifts obtained by jointly fitting the photometry and the spectra are shown in purple. 2 of our targets are well detected. Our quiescent candidate at redshift 3.8 is clearly detected in the continuum and shows H-gamma and H-beta absorption. Our redshift 3.6 candidate shows broad redshifted H-beta O3 emission with a velocity offset of about 1,300 kilometers per second, which indicates a pretty significant outflow at these redshifts. The other 2 spectra are lower signal to noise, so their redshifts are tentative. While these spectra are low signal to noise, I want to emphasize that these 2 objects are detected. We tested this by looking at their spatial profiles. The top panel shows the profile of our redshift 3.8 quiescent galaxy, which is well detected in the continuum. It shows a very clear peak and the negative traces corresponding to our dither pattern. The second and third panel show the profile of the redshift 4.7 quiescent candidates and the profile corresponding to a blank region of the same spectrum. Both of these are normalized to the peak flux of the top one here so that we can compare them. And you can see that the profile of the redshift 4.7 candidate also shows a clear peak and the negative traces, although it's broader because this is a fainter target. And so, while these fainter sources are detected, the redshift solutions derived from fitting both the spectra and photometry are very broad, as you can see in these panels. So I want to highlight again that this indicates that the spectra aren't adding much information to the fit. So we observed each target with Mossfire for 11 hours. To double the signal to noise of these faint sources, we would have to quadruple the exposure time, which is simply too expensive. So to answer the question I posed earlier, no, we cannot reliably confirm quiescent galaxies at redshifts greater than 4 from the ground. So what is the next step for the field? Over the past year, JWST has confirmed a number of quiescent galaxies at redshifts greater than 3, with 2 being at redshifts greater than 4. I'm sure many of you have seen this beautiful spectrum of a massive quiescent galaxy at redshift 4.6 from Adam Carnell. Its spectrum shows a Balmer break and deep Balmer absorption lines, which are necessary to determine a spectroscopic redshift to within 1%. We have an approved Cycle 2 program to follow up our massive quiescent candidates with near spec. Our strategy is to go a little bit deeper than previous JWST programs to obtain not just robust redshifts, but a detailed characterization of their chemical abundances. And so there'll be more to come on this in the next few months when we get our data. Until then, we can speculate on the implications of our Keck Mossfire observations on future surveys and on galaxy formation at high redshift. If our galaxies are indeed at the redshifts that we derived, this is where they would lie on the plot that I showed earlier, and that would make them some of the highest redshift massive quiescent candidates to be confirmed. The K-band magnitudes of spectroscopically confirmed quiescent galaxies at redshifts 3 to 5 are shown here in this plot. The ground-based observations, again, largely derived from Keck, are shown in gray, and those from JWST are shown in cyan. Spectroscopic confirmations, unfortunately, have been limited to the brightest objects, which tend to be young. This introduces an age bias into population studies at these redshifts. Older objects would have higher mass-to-light ratios, and hence be fainter. Our targets are 1 to 3 magnitudes fainter than others in the literature, which suggests that their stellar light is dominated by older stellar populations. This is corroborated by the arrest frame UVJ and synthetic UVI colors. The arrest frame colors of our galaxies are consistent with 1 to 2 billion-year-old populations. Our results, as well as the recent observations from JWST, all suggest the existence of an older quiescent population at these redshifts, which we can now detect because we are pushing towards fainter magnitudes. This also has implications for galaxy formation at high redshift. In 2016, we realized that there was a discrepancy between the stellar masses of the most massive galaxies in our largest photometric surveys, those are the colored points, and predictions from theory, those are the colored lines. And in particular, these observations implied abnormally high conversion rates from baryons into stars, given predictions from lambda CDM. Now with JWST, we've uncovered massive galaxies at redshifts 8 to 10, which push against these limits, further straining tensions with theory. Our most massive candidate, which is coincidentally our highest redshift candidate, tells a similar story. Depending on the assumed number density, if the stellar mass and redshift of this candidate are correct, it would require about 98% of its halo baryons to be converted into stars. And indeed, when we look at the star formation history of our highest redshift candidate, we see that it formed 50% of its stellar mass by redshift 9 to 10. So if its stellar mass is correct, and if its redshift is correct, this redshift 4.7 candidate would be especially profound because it would mean that these tensions with theory may no longer be just a redshift 10 problem. So again, this is all quite speculative given how tenuous the redshift is and given how low signal to noise the spectrum is. So we will need to test this with higher signal to noise spectra, which we can only obtain with JWST. So in summary, I've presented some results from the Phoenix survey, which employs 2 custom filters to increase the sensitivity to the Balmer break of quiescent galaxies at redshifts greater than 4. We used 11-hour Keck observations to report spectroscopic confirmations of 1 quiescent galaxy at redshift 3.8 and 1 broadline AGN at redshift 3.6. The broadline AGN has a velocity offset in H-beta O3 emission of greater than 1,000 kilometers per second, which indicates a pretty significant outflow at these redshifts. Our other 2 candidates had very tenuous redshifts given their low signal to noise spectra. And in particular, our redshift 4.7 candidate indicates that robust spectroscopy of redshift greater than 4 quiescent galaxies is unfeasible from the ground. There are a number of very interesting conclusions that we can draw about galaxy evolution in general based on this population. However, these will all require further testing with incoming data that we have from JWST. So thank you for your time, and please feel free to reach out to me on the Slack if you have any questions about any of this. Thank you.